Okay, so in this video, we're going to look at angular momentum, still making that connection between linear to rotational by just simply using this radius piece. And so any object, again, that is moving, whether it be linear or rotating, has a momentum, right? Again, remember, momentum is inertia in motion, right? And so that would kind of make angular momentum moment of inertia in motion. Okay. Um, So again, if you think about the way we did define linear momentum, we said it was inertia of motion, so a mass moving with a speed, right, or velocity. Well, angular momentum is kind of the same way. It is moment of inertia because that is your rotational equivalence to mass in motion, right? And so the definition of angular momentum is defined as the product of an object's moment of inertia and its angular velocity, or yes, angular velocity. Now, mathematically, it's simply L, right, equals I omega, right? But because we do make this connection back to the linear, right, momentum is mv, so angular momentum is simply mvr, okay? The unit for angular momentum is kilograms times meters squared per second because it's really mass times if you go through and do your, you've got the kilograms times meter squared, you have radians per second, okay, and so that's why you get that kilograms times meter squared per second. Okay, so objects with high moments of inertia and objects with high angular velocities will have rather large angular momentum, right, or high momentum. So you could say L is directly proportional to I, L is directly proportional to omega, but I is inversely proportional to omega. And that's going to play a very important role in conservation of angular momentum, which is going to be the next video. So here's an example. It says, what is the angular momentum of Earth? Assume that the Earth to be a solid sphere rotating about its axis, which I is 2/5 mr squared. Um, the mass of the Earth is 5.79 times 10 to the 24th kilograms, has a radius of 6.376 times 10 to the 6th meters, and it rotates about its axis every 24 hours. Well, we already have these numbers. We did this in the previous video. So we found that the omega for Earth was 7.27 times 10 to the negative fifth radians per second. And we found that its moment of inertia was 9.71 times 10 to the 37th kilograms times meter squared. Okay, so all we have to do here is multiply these two. L equals I omega, and so it's going to be 9.71 times 10 to the 37th times 7.27 times 10 to the negative fifth. Okay, and our um, angular momentum, again, high moment of inertia, relatively low angular speed, but it produces a high angular momentum, right? So 7.06 times 10 to the negative 33 um, kilograms times meter squared per second. Okay, and again, now, so what happens is this radians is actually just technically a unit of one. And so that's why radians doesn't appear in the unit for this, is because it's 1/seconds. Okay, and that's why your unit ends up being kilograms times meters squared per second. Okay, now because there is that rotational equivalence, right? We do have to talk about essentially a rotational impulse momentum theorem. So when you push a merry-go-round, spin a bike wheel, open a door, you're going to exert a torque on that object. Um, if the torque you exert is greater than the opposing torques, right? So if I start spinning and it's greater than what will oppose that motion, then the rotation increases and the angular momentum will also increase. And I'm going to guess this to say the rotational speed increases, um, which makes the angular momentum will increase as well. So the greater the moment, excuse me, the greater the net torque, the more, uh, this is the word here is the quicker or more quick the increase in L, or the greater the increase is. So mathematically, you get that um, rotational equivalence, right? So if you remember impulse momentum theorem, it was not J, we'll call it delta P equals F delta T. Well, the rotational equivalence of P is L. The rotational equivalence of F is torque, right? Tau, and then time doesn't care about rotate the if it's rotating or moving linearly, right? It just matters that a stopwatch has been started and it's been stopped. Okay, so now here are just two examples using this equation. Okay, and so this says here the figure shows a lazy Susan food tray being rotated by a person in the quest of sustenance. Sustenance just means food. Suppose the person exerts a 2.5 Newton force perpendicular to the lazy Susan's 0.260 meter radius for 0.150 seconds. What is the final angular momentum of the lazy Susan if it starts from rest, assuming friction is negligible? What is the final angular velocity of the lazy Susan given that its mass is 4 kilograms and assuming its moment of inertia is that of a disk? Okay, so first part of the question, we're going to do our rotational equivalence to impulse momentum theorem, right? So change in angular momentum is equal to torque times delta t. Well, how do we find torque? RF, right? So it's going to be RF delta t is going to equal the change in the change in angular momentum, but change in is L minus L0. But they tell us that it starts from rest, so the L0 will be 0. And so this just gives us our final angular momentum is just going to be multiplying R times F times delta T. So we're going to do R, which is 0.260, times F, which was 2.5, and we apply it for 0.150 seconds. Okay, and so once we do that, we get an angular momentum of 0.0975 kilograms times meters squared per second. All right, sorry for the change in levels there, ran out a little bit of space. And so now this becomes our L for L equals I omega to find the final angular velocity. So omega is going to be L over I, but we need to find I. For a disk, the um, the moment of inertia is 1/2 mr squared. So we're going to do I equals 1/2 times 4 times 0.260 squared. And so that's going to give us a moment of inertia of 0.1352 kilograms times meter squared. And so now we just plug that in, 0.0975 divided by 0.1352, and that will give us an omega of 0.721 radians per second. Okay, so after applying a force of 2.5 newtons, this lazy Susan will now be rotating at 0.721 radians per second. All right, next question. A lot of times students always ask, why do I take physics if I want to be a doctor? Here's an example, right? You can see here, this is talking about a leg and the femur and the muscles and the ligaments, okay, here. And so this says the person whose leg is shown in the figure kicks his leg by exerting a 2,000 Newton force with his upper leg muscle. The effective perpendicular lever arm is 2.20 centimeters. Given the moment of inertia of the lower leg is 1.25 kilograms times meter squared, find the angular acceleration of the leg, and then neglecting the gravitational force, what is the rotational kinetic energy of the leg after it is rotated through 57.3 degrees, which is 1 radian. Okay, and so what we're going to do now is we're going to do torque equals I alpha, okay, where alpha is torque over I, and so it's going to be RF over I. And so this question kind of just puts together all of this conversations about torques and so forth. And so they tell us that um, a radius of 0.02220. Sorry, that looks like an 8. I always think that I'm just writing with the regular pencil and I can write over it and heavier and it will look normal. Um, apply a force of 2,000 newtons with a moment of inertia of 1.25 kilograms times meter squared. And so the angular acceleration of the leg will be 35.2 radians per second squared. Okay. Now, why do we need that? Because that's going to help us find the final angular velocity, right, of this object. And so we go back to those kinematics. So they give us delta theta. They give us, or we have alpha from our first part, and then we know it's going to start from rest. So omega is going to equal the square root of 2 alpha delta theta. And so it's going to be the square root of 2 times 35.2, right, times delta theta, which is 1, because it tells us 1 radian is 57.3 degrees. And so our omega will be 8.39 radians per second squared, or radians per second. And now we use that to find our kinetic energy. So 1/2 I omega squared, it's going to be 1/2 times I, which is 1.25, times 8.39 squared. And so our kinetic energy for the leg will be 44.0 joules. Okay. So in the next video, it's gonna be our last video for this unit, and we're gonna look at conservation of angular momentum. Just remember that just like linear momentum, angular momentum will always be conserved.